Welcome back to lecture 17.1, where we're going to do, let's just call it more Carnot. Okay. So hopefully you had a nice midterm, so that lecture 16 was taken up by the midterm. Hopefully everything went smoothly. This time I want to get back, remind ourselves a little bit about what we were doing before the midterm or what we were doing on the midterm. And then we'll move into some new material. So we've been talking about Carnot cycles, the efficiency in a Carnot cycle, the refrigerators, and heat pumps. So let's just remind ourselves that our Carnot cycle was composed of isotherms and adiabats, right? So these are isotherms, for example, at TH and TC. And these are our adiabats here and here, okay? So we had heat that would flow in and heat that would flow out. Okay, so, right, we had heat coming in from a hot reservoir. So the other way we looked at it, I think I'll just write it underneath and maybe we'll keep this. We had a hot reservoir and a cold reservoir, and we had an engine. And let's call it a Carnot engine for now. We had the heat come in, QH, and the heat go out, QC. And this did some work, and we had an efficiency, eta, which was defined as the work over the heat put in. Which was QH minus QC over QH. And this was always less than equal to V1. And we actually showed that for an ideal gas, that QH over QC was equal to TH over TC. And so we could rewrite this as eta was 1 minus Tc over Th. Okay, so the question, we kind of talked about it before, but I want to be a little bit more detailed on, is whether or not we could do better than this Carnot cycle. Okay? We just wrote down, we defined this Carnot cycle, told you that it was made of isotherms and adiabats, and now I want to know, could I do better than a Carnot cycle? Okay, so let's imagine doing the following. Let's imagine building two engines, right? Both with the same heat reservoir. Both a hot reservoir and a cold reservoir. And so let's put a Carnot cycle, a Carnot engine, I mean. And imagine having some heat come in, having some heat go out. And let's imagine having some work done, but also imagine we could build a better engine, right? Imagine if we could build a better engine than a Carnot engine. We could call it, let's say, a super engine. So let's connect it to the same reservoir, QH and QC, and get out some work. Okay? let's assume that these are different quantities because this is a different engine. Okay? Now, I want to imagine doing the following. I've got a Carnot engine and a super engine, both running from the same thermal reservoirs. But now I want to take my Carnot engine and I want to run it backwards. Okay? Let's imagine running it backwards so that QC and QH and work. Okay, so what is this one now? It's running as a heat engine, right? Sorry, a refrigerator or a heat pump. Okay, so now let's imagine connecting our two, right? So that we are going to drive our super engine. It's going to drive the Carnot cycle. Okay. And I could call this W prime, but it doesn't matter which one I call it because I'm going to connect this one to this one. So if this were different, then yeah, we can call it W prime. That's fine. Okay, so you're still going to get some heat out. So let's imagine the efficiency of the Carnot cycle. So our Carnot should be W prime over Q. Sorry, it should be. If we were running it as an engine, it would be W prime over QH, and the super would be W prime over QH prime, right? Because I'm inputting a different amount of heat. So if we could build an engine which was more efficient, right? We had a super that was greater than the Carnot efficiency. That would mean that our work prime over QH prime would be greater than our work prime over QH. Which would imply, right, that QH prime is less than QH. Okay, maybe that seems reasonable so far. Well, there was no net work, right? Because all of the work produced by our super went into our Carnot. But QH, so we're drawing less power. So drawing less heat from TH, from the hot reservoir. Than depositing back in. Okay, that seems fine. Because, wait, what are we doing? We're drawing heat from, where is that heat coming from? Oh, it must be coming from the cold reservoir, right? So, what are we doing? We're drawing heat from the cold reservoir and depositing in the hot reservoir, but we're doing no work. And this is the problem. Remember, this violates the second law of thermodynamics. You cannot have a process where you spontaneously take heat from the cold object and flows to a hot object. All right? This is a violation of the second law, and it's a violation of common sense, right? You know that that heat doesn't flow from cold to hot. It flows from hot to cold. So this says that all Carnot cycles, right, have the same efficiency. That's why we could say, we're going to be able to say, no matter what the Carnot cycle is, it can have this, right? We solve this for an ideal gas, but the point is that all Carnot cycles are identical, have identical efficiencies, right? And this allows us here to say something important, right? So we can actually use this, and your book says you can use this to define a thermodynamic temperature. That is, that you can have a temperature which is entirely dependent on heat and heat flows, assuming that QH and QC are reversible. Okay. So let's stop there with our Carnot efficiency, and we're going to go on, and we're going to talk about a little bit more about some of our first and second law.